I'll be talking about angular momentum for rigid bodies, and uh, first I'll start with some theory, and then I will cover two examples. So yeah, let's start. So the formal definition of angular momentum, uh, L, which is a vector of a particle, is defined as L is R cross P. So this is a vector cross product, and R is the position vector of the particle with respect to a point O. So as you can see, the angular momentum is definition needs point. So it is basically calculated with respect to a point. Yeah, so it is R cross P, and P is the momentum vector, which is m mass time velocity vector. So yeah, so L depends on the position vector R, and hence the choice of the point O. And the direction of L is same as the vector cross product of R cross P, and it is given by right hand rule. So you might have already learned about the right hand rule. What you do is point your index finger, the finger next to thumb, along R, and orient your hand so that all other fingers bend towards P. In that case, your right hand thumb will be pointing in the direction of angular momentum. So if in this picture, if you see R and P are on the xy plane, then angular momentum L will be pointing in the z direction. So this is all about angular momentum for a particle, uh, but the same concept applies when you go to a rigid body. We will be talking about motion which involves both translation and rotation. Example, a drum rolling down an incline. So a drum is rotating around its axis, and its axis is undergoing translation motion down the incline. And it is always possible to describe any motion of rigid body by a translation of its center of mass plus a rotation around its center of mass. So yeah, it's a superposition of translation and rotation motion. So I haven't, I won't be going through the detailed derivation, but if you assume the rigid body to be made up of n particles, you can derive this expression, and what it means says is that the total angular momentum is r cross m v com. So this is a velocity vector of center of mass, and this is the position vector from point O to the center of mass. Then plus we have another term which represents the angular momentum due to motion around the center of mass of the body. And this rj prime vector is the position vector of the jth particle with respect to its own center of mass. So the first term is angular momentum due to the motion of center of mass, and the second term is angular momentum due to motion around the center of mass. So this expression is a little complicated, and I won't be going through that in detail. Um, but I want to show a simplified case of uh, 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 where we find the z component of angular momentum. So if you see here, I'm trying to find only the z component, and so this vector I take the z component, and this expression, if I assume the motion of the particles around the center of mass, uh, uh, basically it's a rotation. So if I assume that the axis of rotation is in z direction and passing through the center of mass. So for this term, right, the axis is the z-axis passing through the center of mass, then this simplifies to I naught omega. So so basically this is I naught omega, this term, and then this is just coming from the spinning of the body around its own center of mass. So where I naught is the moment of inertia of the body around the z-axis passing through center of mass, and omega is the angular speed of the body around its center of mass. And the first term is the angular momentum due to center of mass motion. Uh, we also call the first term as orbital angular momentum, and the second is the spin angular momentum. Uh, and this is similar, like it is easy to understand this by thinking about the Earth's motion around the sun. So you can see the um, Earth is spinning around its own axis and completes one rotation in a day. At the same time, it's also doing orbital motion and takes 1 year to complete one rotation around sun. So yeah, so the orbital motion is the first component, and the spin motion is the second component of the angular momentum. So I'll be showing two examples, but we will limit ourselves to the situation where the axis of rotation is along the z-axis, uh, and the orbital L also is entirely along z-axis. But even if it is not, we can take the z component. But I think in the example I will be showing, even the orbital angular moment is entirely along z-axis. So it's we can to find a total angular momentum, we can just add the two terms. So yeah, so I think it's will be good to remember this formula. In that case, L is uh, uh, so assuming that uh, the R and V are perpendicular, and they are lying on the xy plane, then the angular momentum will point in the z direction for the orbital part. So the magnitude will be r times so mass and vcom. So vcom is the velocity of center of mass plus I naught omega. And this I naught omega is the angular momentum due to rotation of the rigid body around its center of mass. So I think it's important to remember this formula. Okay, so we'll just go to the first example. This was asked in 2021. So we have a thin rod of mass m, length a, is free to rotate in horizontal plane about a fixed axis, passing through point O. So yeah, as I said, we need to know the point for calculating the angular momentum. A thin circular disc is pivoted on this rod with the center distance a by 4 from the free end. You can rotate freely about the vertical axis. Okay, so the rod is rotating around axis passing through O, and the disc is also pivoted to the rod, so it is also rotating. In addition to that, it is also rotating around its own axis, which is passing through its center of mass. They remain during the, and this is it's horizontal. So basically, we can assume it's xy plane. So the angular momentum will be in z direction, so we can use the this particular formula. Okay. Outside stationary, observe the rotating with angular velocity omega, and disk rotating 4 omega. Okay, so disk is rotating around its own axis with angular velocity of 4 omega, and the rod plus disk they are rotating around the axis passing through O with angular velocity omega. And then we have to find the total angular momentum. Okay, so yeah, first thing, we can always find the angular momentum of two different rigid bodies separately, and we can add them vectorially. However, here both angular momentums are in z direction, so we can just add their magnitude. So first, for the rod, it is easy. uh, so it is I omega for the rod, and the I is the moment of inertia about the axis passing through one end of the rod, and it is ml square over 3. Basically, ml square over 12 is through about the axis passing through the center, and then using parallel axis theorem, you can find it's ml square over 3 times omega. uh, okay, there's no length is actually a, so yeah, let me change that. So ma square. Okay, and then for the disk, we can use this formula. So for the L disk, so m mass is m, radius, it's not the radius, it's a distance from point O to the center of mass of the disk, and that is 3a over 4. And velocity of center of mass. Okay, so the center of mass is rotating around O with angular velocity omega, and it's the center of mass is at a distance 3a over 4, so that is the velocity of center of mass. So this is the first term, and I naught is half mr square for a disk. So r is here a over 4, and its omega here is 4 omega. Okay, so the first term is ma square omega 9 over 16. Then this is ma square omega 1 over 8, and this is okay. So the total angular momentum, you add all the three terms. So LCM is 48, 16, 27 plus 6, 33. Yeah, so it is 49 over 48 ma square omega, and in this question they're asking for n, so only 49 is missing, so yeah, n is 49. That's the answer. So I just wanted to add one more point here. So if in this question the circular disk was not spinning about its axis with 4 omega, and it's just the rod plus disk combination was rotating around O with angular velocity omega, then we would have used parallel axis theorem for the disk as well. So the rod we already found ma square over 3 times omega, and for the disk we would use parallel axis theorem, so it is half mr square, which is a square this, and then parallel axis theorem says mass times the distance from the point O, so square, so which is 3a over 4 square times omega. So this would have been the disk angular momentum, and then you would have added to the rod, and that would have been the answer. But here it is spinning, so let's anyways find this. So this is ma square omega, and then we should also add the L rod. So L rod is 1/3. So I think 96. So this is 89/96. So yeah, you can see that the angular momentum is a little smaller than the previous case, where the disk was also spinning, and it makes sense. Okay, this is another question I want to go through. It was asked in 22. So here a flat surface of thin uniform disk is glued to a horizontal table. So this is stationary and glued. Another thin disk B mass M radius rolls without slipping on the circumference. A flat surface of B also lies on the table. Okay, so we can assume it's all is xy plane, and then angular momentum will be in z direction. So we can again use this formula. Okay, the center of mass has a fixed angular speed omega about the vertical passes through the center of A. Okay, so this is center of mass of B, and it is revolving around A with the angular velocity omega. So that is omega. The angular momentum of B is n omega square. So we have to find a total angular momentum. Uh, and then it's mentioned that this disk B rolls without slipping. So it is also spinning, and it is the angular velocity of spinning is not given in this question. So we'll assume it's omega prime, and we need to find omega prime in terms of omega. These are same radius, so R. So this is R, and this is another R. Okay. There are many ways to find omega prime. I will use the fact that P is rolling without slipping. So what it means is a point of contact between the two surfaces. It's at instantaneous rest, meaning the net velocity is zero. So there are two velocity components acting on this point of disk B. One is due to the velocity of center of mass. So center of mass of B, it is moving with speed which is omega times the distance of center of mass from A, which is 2r. So this point of on disk B is moving in this direction with omega 2r. Let's say the disk also disk B rotates around its own axis with omega prime. The tangential velocity due to rotation around its own axis will be in this direction, because omega prime is counterclockwise. So this will be omega prime times the distance of this point from its own axis, which is r. So the net velocity has to zero, should be 0, so omega 2r minus omega prime r is 0. So that tells disk B is rotating around its own axis with angular velocity 2 omega. And after that it's straightforward. We can just plug in the values. So m is m and the r is the distance from the point the angular momentum needs to be calculated, and which is the center of disk A. So the distance of from center of A to the center of mass of B is 2r, and velocity of center of mass of disk B, as we said earlier, is omega times 2r. Okay, and then the second term is I naught, and for the disk it is half mr square, and the omega is the omega velocity around its own through the axis passing through its own center of mass, and we just found it's 2 omega. So that's all. So the first term is 4 omega square r, sorry, omega r square, and this is mr square omega. So we get 5 m omega r square. So 5 is the answer. Now in this question also we can make a small modification and see what how to go about it. So so here the disk B is rolling without slipping. What if it does not do that instead? So let me mark a point. So let me, with the ink I can mark a point here on this disk B, and let's assume that the disk B rotates in such a way that this point is always very close to the it's basically in the same position with respect to disk A in all throughout the motion. So for example, when the disk B is here, the red point is here. So and then similarly when it is here, the red point stays the same with respect to point A. So in that case we can like in the previous example we can use parallel axis theorem, and we can calculate the angular momentum, which will be I omega. So the I is half mr square plus mass times the distance of center of mass of B from the center of A, which is 2r, and times omega. So this is 4r square, and this is half, so it's a 4.5. So it will be 9/2 mr square omega. So yeah, I mean D would have been the right answer in this case. Another way to solve this question is to use this formula, which says L is mr VCOM plus I naught omega. So the first term will still be 4m omega r square. Nothing changes there. Now you might think that the way I've shown the red crosses, the disk B is not spinning. Actually it is it may not be that obvious, but disk B is still spinning, and its angular velocity is actually omega. So I naught is half mr square times omega. So you'll still get 9/2 mr square omega. And the way to see that, why the disk B is still spinning, you can see the center of mass here. With respect to center of mass, the red cross is southwest direction, but here it's in northeast, and if you come here it's northwest direction. So with respect to center of mass, the red cross is still moving, and once it makes a full circle around A, the red cross also would have made a full circle. So that's why the disk p angular velocity around its own center of mass is actually omega. So you can use either the parallel axis theorem or the same equation what we derived for translation and rotational motion here, and you'll get the same answer by using either approaches. So yeah, I think yeah, just remember this expression, and you can use it to calculate angular momentum when there is both translation and rotational motion involved.